Okay, hi guys. Today we're going to be looking at one of my absolute favourite things in maths, and that's called Pascal's triangle. Pascal's triangle is just one of these really great naturally occurring patterns that we have, and we did mention it briefly the other day in class. So here it is. Cool, my virus there we go. My virus protection has gone. So I'm just going to write out the first 6 rows of Pascal's triangle. So hopefully what you can see is you get each row of Pascal's triangle by adding together the 2 consecutive numbers in the part before it. So if we look at the 6th row, we get that from row 1 plus 5 is 6, 5 plus 10, 15, 10 plus 10, 20, 5, 10, 15, etc., etc. Pascal's triangle has all these lovely patterns in it. Like if we look down on our diagonals, our first diagonals, we can see there these are just our natural counting numbers. They're all our integers. We can also look at the second row. These are all what we call triangular numbers because they actually make triangles. So there's 3, there's 6, there's 10, 15. They all make triangles when you draw them out. There's another really nice pattern here, which is triangles of square numbers. So 4 squared gives us 16, and 10 plus 6 gives us 16. 5 squared is 25, and 15 and 10 is 25. 3 squared is 9, 6 and 3 gives us 9, and we can kind of see that pattern going down as well. The last one, which is really important, is that this Pascal's triangle can also be made from powers of 11. So 11 to the power of 0 is 1, 11 to the power of 1 is 11, 11 to the power of 2 is 121, 11 to the power of 3 is 1,331, 11 to the power of 4 is 641. If you don't believe me, check it out on your calculators. All right, Pascal's triangle's biggest application for you guys is going to be in terms of binomial distributions though. So if we take like a really simple binomial distribution, such as tossing a coin, if we toss one coin, we can end up with a head as an outcome or a tails as an outcome. If we toss 2 coins simultaneously, we can end up with 2 heads, a heads and a tails and a heads, or 2 tails. We can see here we have a 1, a 2, because these options are really kind of the same, and a 1. If we look at 3 coins, we can take 3 heads, 2 heads and a tail, 2 heads and a tail, 2 heads and a tail, 3, 1. We can have 2 tails and a head, 2 tails and a head, 2 tails and a head, another 3 there, and then the last one, 3 tails. 1, 3, 3, 1. Exactly the same as our third row of Pascal's triangle. And this continues to be the repeating pattern. When you're looking at what we call a binomial distribution, obviously binomial meaning 2 outcomes. Okay, so where we're looking at a pattern where we've got 2 different outcomes, such as tossing a head or a tail. For you guys, Pascal's triangle is going to come mostly into application when you're looking at expanding brackets of a binomial expression. So again, I'm just going to write this out to there we go, up to the 6th line. Okay, so say we want it to expand. Because we're talking about heads and tails, we'll talk about h plus t all squared. Now, you could FOIL it, and you'd get head squared plus heads tails plus tails heads plus tails squared, or head squared plus 2 lots of heads times tails plus tails squared. 1, 2, 1. 1, 2, 1, same as in Pascal's triangle. If we were going to look at heads plus tails cubed, we could take our heads plus tails squared expression, multiply it by another heads plus tails, and again you could FOIL it, and you'd get heads cubed plus 2 heads squared tails plus heads tails squared plus heads squared tails plus 2 heads tails squared plus tails cubed. Again, you could simplify that because we've got heads cubed there, then we've got 2 lots of heads tails, 1 lot of heads squared tails there, so that makes 3. Then you've got heads tails squared, another lot of heads tails squared, so that again makes 3 heads tails squared, and then tails cubed at the end. Again, 1, 3, 3, 1, 1, 3, 3, 1. Okay, foiling, once you get past a cubic, becomes a really, really ineffective way of expanding. And I'm going to give you guys the example, and instead of using FOIL, we're going to use Pascal's triangle instead. So we're going to look at heads plus tails to the power of 5. Now, if we're looking at the power of 5, we're going to use our 5th row of Pascal's triangle, which is 1, 5, 10, 10, 5, 1. The first thing I'm going to do is write those numbers in. So we're going to have 1, 5, 10, 10, 5, and 1. We're then going to take our first letter in here, which is H, and we're going to start off with H to the power of 5, and then each term you're going to decrease that by 1. And then in the last one, we're down to 0, so we don't write that in. We're then going to take our second letter, or our second variable, which is t, and we're going to start from the back, and we're going to start off with 5. And then, t, we're going to start off with 5, and then we're going to decrease that by 1. Again, in the first one, 0. Okay, from there, we can just add in plus between all of them. It's always going to be plus. And we can simplify, so we don't write the 1, so we're going to have h to the power of 5 plus 5h for t plus 10 h cubed t squared plus 10 h squared t cubed plus 5h t to the power of 4 plus t to the power of 5, and that's our solution. Okay, much easier than expanding h plus t, 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 right? Which would be an absolute pain in the ass. Okay, cool. I'm going to show you one more kind of harder example, which will hopefully convince you even more, and then we'll be done. So, new page. Again, I'm just going to write Pascal's triangle in here. So we're going to have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, we're not going to do a power of 7, but I've written it in there just because I always think it's handy to go kind of one row more than what you're using. So we are going to be looking at a power of 6. And in this time, we're going to expand something that's a little bit harder. So we're going to expand 2x minus 3 to the power of 6. Right, so again, the first thing I'm going to do is I'm just going to write in all of the coefficients. So we're going to have 1, 6, 15, 20, 15, 6, 1. Hopefully I got enough room there. Okay, we're then going to start from the front, and we're going to have 2x. We're going to start off with the power of 6, and then every time we do this, we're going to decrease it by 1 until we get down to 0. Again, we're then going to start from the back. We're going to put in negative 3 to the power of 6. Ooh, I'm just running out of room. When you guys write this out, please write it out better than what I'm doing it here. This is atrocious. Oh no, I did 4 twice. Hang on, sorry. I've written in power of 4 twice. I got to the end and I was like, I shouldn't end up with any green at the end. There you go. And that's kind of what you should be thinking about. So we've got 6, 5, 4, 3, 2, 1. I'm so focused on how messy it was. Okay, all right. So now we're just going to add in, again, we're just going to add in a positive between all of those. Now, hopefully what you should notice is that you've got a negative number here. So not all of these are going to be positive at the end, but whether they're positive or not depends on whether the power on the negative number is odd or even. Because if we know that like negative 2 times negative 2 is positive 4, all of our ones where we've got an even power, such as a squared or a quartic or a power of 6, they're all going to be even. Anywhere we've got an odd, like 5, 3, or 1, are going to be negative. Okay, so 2 to the power of 6 is 64, so we're going to take 64, why am I writing 3? 64 x to the power of 6, that's our first term. We're then going to take 2 to the power of 5 is 32, 32 times 3, let's do this on the calculator, so we have 32 times by negative 3 times by 6. Okay, negative 527. Okay, so that's going to be negative 527 x to the power of 5. Okay, we're then going to take this one's a square, so this one's going to be positive. So we have 9 times 16 times 15. So we can chuck that in there, 16 times 15 times 9. That's going to give us 2,160. This one's got a negative power. So this one's got an odd power of power 3. So this one's going to be negative. So we're going to have 20 times 8 times 3 to the power of 5. So 20 times 8 times 3 to the power of 5. Okay, that's going to give us 38,880. What was it? 38,880. What am I doing? 880 x. What are we up to? X cubed. We're then going to have 15 times 4 times 81. So 15 times 4 times 81. 4,860. We're then going to have 6 times 2 times 3 to the power of 5. So 6 times 2 times 3 to the power of 5. Okay, 2,916. And then we're going to have plus 3 to the power of 6. Okay, 729. Okay, now again, I've made 2 little mistakes here. I just realized the first one is, again, that's an odd power, so this one's going to be negative. And the first one was, I think I times that by 5 because that looks like a 5 on there, but it should actually be a 3. So I'm just going to go up. I just realized I've done it on the calculator up here, so I'm just going to take this one. Just going to change that to a power of 3. And I thought it seemed too big, and we're going to get 4,320. So I'm just going to change that to 4,320. Okay, and again, that should be a 3, not a 5. It's just kind of hard to tell. Okay, all right, so there's our expansion. Again, it's a really, really hard expansion, but if you tried to expand that out 6 times, I guarantee you there would be a lot of errors. Okay, all right, hopefully that helps. Try a couple yourselves. Okay, bye.